All right, hello and welcome everyone. My name is Ali, and on behalf of my collaborators, Drew Sharma and Professor Florian Shkurti, I'm honored to present our paper for ICRA 2022 titled Augmenting Imitation Experience via Equivariant Representations. Okay, so let's jump right in. So the main motivation for this work is that behavior cloning suffers from this common problem of drift. By definition, expert data doesn't contain any mistakes, and therefore can't really teach you how to recover once you've already made a mistake. For example, let's think about the problem of driving. In their paper, End-to-End Learning for Self-Driving Cars, NVIDIA used data from 2 additional cameras with adjusted ground truth labels to stop the car from drifting off of the road. This approach can work pretty well, but adding additional sensors to your system can be inconvenient and also quite expensive. So the question that naturally arises is that can we make visual navigation using a single camera more robust? In our paper, we aim to approach this problem using the concept of equivariance. Essentially, equivariant features are features that change predictably with respect to some transformation applied to the original input image. That means if you have an image and some learned features, and you then apply some transformation on the image, if you can find a corresponding transformation to apply to the features to describe how they would change, then those features are said to be equivariant with respect to that transformation. So here's our process in a nutshell. We collect navigation data with multiple cameras, and using neural networks we learn image features or embeddings that are equivariant with respect to the different viewpoints of the cameras. This allows us to predict now for a single camera what its embeddings would look like from those other viewpoints. We can then use these additional embeddings to augment the training dataset of a navigation policy that's trained on a single camera that maps image embeddings to control actions. This makes the navigation policy perform a lot better. To evaluate our method, we perform a number of experiments. In each of them, we train 3 policies, one using data from just a single camera, another using data from multiple cameras, and lastly, a policy trained using data from just a single camera, but augmented with our predicted embeddings to compensate for the missing cameras. So this is the setup for our simulation experiments. We test behavior cloning navigation performance, that is, how well can the learned policy match the expert trajectory. We do this for a ground vehicle with 3 cameras and a flying vehicle with 5 cameras. Here are the results of those experiments. As you can see, in both cases, the augmented policy performs better than the single camera only policy. Now let's move on to what I think are our coolest experiments. These are the experiments we performed on a real-life ClearPath Husky robot tasked with navigating a 600-meter path at the University of Toronto. The setup is analogous to the driving simulation experiment. Here it is navigating using a policy trained only on a single camera. As you can see, it doesn't have the best performance, and it drifts off of the road from time to time. Now, let's compare that to navigating using a policy trained using our equivariant augmentations. As you can see, it's quite a bit more robust and immune to some of the pitfalls that the previous policy suffered from. Here's a snapshot of the results of those experiments. As you can see, the policy trained using a single camera alone had 9 interventions all over the place, and the policy trained using our equivariant augmentations matched the results of the policy trained using all 3 cameras, which both only have 1 intervention at roughly the same spot, which is a pretty cool result. So, in conclusion, our approach allows us to learn features that are equivariant with respect to viewpoint transformations, and then use this to augment the training set of imitation learning policies for visual navigation. And our experiments show that visual navigation performance can be significantly improved by using these equivariant augmentations. Alright, that's it for me. I hope this video was helpful. Thank you for watching and have a wonderful day.